Okay, the notes for 4.5, transformations of other trigonometric functions. So in 4.4 we talked about the transformations for sine and cosine, and in 4.5 we're going to talk about the rest of the trig functions. So we'll have tangent, cotangent, cosecant, and secant. And one of the reasons that we can group these four together is because these four will all have asymptotes. Okay, so we're going to look at the four remaining trig functions, and that will be y equaling a tangent of bx minus c plus d, y equaling a cotangent of bx minus c plus d, and then y equaling a cosecant of bx minus c plus d, and y equaling a times the secant of bx minus c plus d. Now if you remembered when we graphed the parent functions, cosecant we often referred to the sine function when we did the graph first, and with secant we referred to the cosine graph first when we did that one as well. Okay, so we're going to take a look at just a few of the characteristics before we get started. These are a little simpler to draw. Really we're going to base our drawings off of the asymptotes and the movement that they have. So it says in many ways these functions will allow the same transformations as sine and cosine. Below are the starting and ending values of x that you can use to find the starting and ending values of a cycle that has a period change or a phase shift. So starting and ending values of a cycle with a period change and or a phase shift applied to it. So when we think about, first of all, tangent and cotangent. So these are a little bit different than sine and cosine. The period for tangent is simply pi over b. The parent function for tangent just takes one cycle to complete in pi radians, and the cotangent then as well will be pi over b. And again, b will be an absolute value, because if it's negative, that's when we look at a reflection, actually in the y-axis. Okay, so when we look at starting and ending x values, we're actually going to focus on the asymptotes to guide the behavior of these functions. So when we talk about starting and ending x values, we're going to talk about the first, the starting x value or the starting asymptote for tangent. So we can use x equaling pi over 2 and x equaling 3 pi over 2. So when we graph tangent, the parent function, we had the first asymptote at pi over 2 and the second asymptote at 3 pi over 2. So when we have a phase shift or a period change, what we're going to do is we're going to take and set whatever is bx minus c equal to the first positive asymptote, pi over 2. And that will give me the new start when I solve for x. And then we're going to take bx minus c and set it equal to 3 pi over 2, which is the second asymptote. And this will be the new end when you solve for x. And once we have those asymptotes, then we can simply graph them and then create the tangent curve in between. For cotangent, as we know, the cotangent has asymptotes starting at 0, and then the period is pi, so the next asymptote will be at pi. So when we graph cotangent, we're going to start, if we have a shift, if we have something going on in bx minus c, we're going to set the first one equal to 0, and the x here when we solve will be the new start or the new asymptote, and then we're going to set bx minus c equal to pi, and this, when we solve for x, will be the new end. Okay. So then let's finish off with cosecant and secant. So cosecant, as we know, is the reciprocal of sine. That's the same as 1 over sine. And secant is the same as 1 over cosine. So those are our reciprocal functions. We know that the cosecant, being the reciprocal of sine, also takes 2 pi radians to complete one cycle. So to find the period of cosecant, it would be 2 pi over b, and we'll do the absolute value. Now, for cosecant, where the sine function had intercepts will be where the cosecant will have asymptotes. So the sine function started out at 0, so the first asymptote would be at 0, and the second one would be at pi. Again, these are where the x values are 0, and since sine is really y over x, putting that over 0 makes it undefined. So these would be the vertical asymptotes starting out for cosecant. However, when we graph cosecant, we're going to focus more on graphing the sine function first, and wherever those intercepts are, we're going to create our asymptotes. So we'll be very visual when we do that. We're not going to worry about these two here because, again, the way that we're going to graph this will be based off the sine function. When we talk about secant, just like cosine, the secant has a period of 2 pi. So to look at any changes, we would look at 2 pi over the absolute value of b. And then the cosine has intercepts at pi over 2 and 3 pi over 2. So that's where the x is 0, and so when you do the reciprocal of 0, you get undefined. So this is where secant would have vertical asymptotes. So again, when we graph secant functions, we're going to start by looking at the cosine function like we did when we graphed them on the parent function day, and we're going to use the same approach. Okay, so now let's try some graphs. Not as much to these maybe as sine and cosine. So example 1, locate the vertical asymptotes and sketch the graph of y equals tangent of 2x. So as we look at this, if we go along with the VAP procedure that we were doing, this does tend to be a little different, but we can still absolutely use it. There's no vertical shift. The amplitude is 1. So there's not really a top and a bottom, a crest or a trough. So the amplitude doesn't always really come into play with this, but we can always list it. For the phase shift, this is where we're going to take that bx minus c and set them equal to the first asymptote and the second asymptote that we know of for tangent. So I'm going to set this equal to pi over 2 and 3 pi over 2. Well, my b over c is simply 2x, so I'm going to set 2x equal to pi over 2 and 2x equal to 3 pi over 2. So when I divide by 2, that's the same as multiplying by 1/2. Oops. And I'm going to have pi over 4 and 3 pi over 4. So this is my new starting asymptote at pi over 4, and this is the new ending asymptote at 3 pi over 4. So if we look again now at the difference between pi over 4 and 3 pi over 4, that's 2 pi over 4s to get from 1 to 3, and that reduces to pi over 2. So if we do the period formula, it would be just pi over b, and that's pi over 2. So instead of having a period of pi, we're now going to have a period cut in half of pi over 2. So when I did my scale, I did a scale of 30 degrees, or pi over 6. Actually, let's go by pi over, I'm going to do a scale of pi over 6. Nope, I'm not. I'm actually going to do pi over 4. And the reason I'm going to do this, I am going to go every other one pi over 4. So here would be pi over 4, 2 pi over 4, or pi over 2, 3 pi over 4, 4 pi over 4, or pi. And I'm actually going to stop right there because I know that my first asymptote is going to be at pi over 4. So I'm going to graph that. And my next asymptote will be at 3 pi over 4. Now these asymptotes are actually Unlike the box method, they're a critical part of your graph. We absolutely need to see these in the graph. They are a part of it. And then in between, tangent has an intercept at pi over 2. So in between the period, it's going to have an intercept. And then again, tangent curves down and to the right. And so we could just keep repeating and keep repeating by counting by pi over 4s. This would be 5 pi over 4, 6 pi over 4, or 3 pi over 2, 7 pi over 4, 8 pi over 4, or 2 pi. And so we could do a few more of those. We want to go every pi over 2, or 90 degrees. So we would have another asymptote after 3 pi over 4. 2 more pi's over 4 would be 5 pi over 4. 6 pi over 4, 7 pi over 4. And we're just going to leave it right like that. We'll just do one more. So we go right in the middle, and we'll do one down. Okay. And we actually, just for practice, know that we could also go the other way. Here's negative pi over 4. From negative 45 to positive 45 is 90 degrees, or pi over 2. So we could also put an asymptote going to the left with an intercept in the middle. So there's my tangent function. This is the tangent of 2x. Okay, let's look at example 2. We have two equations here. Locate the vertical asymptotes and sketch the graph of each function. So first we have y equaling the negative tangent of x over 2. So this negative will reflect the graph over the x-axis. So we just want to keep that in mind as we create our graph. So let's start with VAP, vertical translation, amplitude, phase shift, and period. So there is no vertical translation. The amplitude is 1, with again a reflection over the x-axis. So my phase shift, I'm going to set equal to, I'm going to take, I'm going to make x over 2 1/2 x, set that equal to my first asymptote, pi over 2, and then set 1/2 x equal to 3 pi over 2, and solve for x to get my new starting asymptotes, or to see that phase shift. Or sorry, this doesn't have a phase shift, the period change. So if I multiply both sides by 2, x is going to just equal pi, and if I multiply by 2 over here on the other side, x will equal 3 pi. So now I have from pi to 3 pi, that's a length of 2 pi. So if I look at the formula for period, pi over b, my b value is 1/2, so pi divided by 1/2 is pi times 2, so 2 pi is the period. So the first asymptote that I'm going to make will be at pi, and I actually do use for this one a scale. I'm going to use a scale of pi over 6. So as we begin to count, 1 pi over 6, 2 pi over 6, 3 pi over 6, let me see, or pi over 2. So 30, 60, 90. I'm actually going to label every 90 degrees, 60, 90, and back this way there's negative 90 degrees, or negative pi over 2. So 1, 2, after 3 more, this is going to be pi, 3 more, 3 pi over 2. 1, 2, 3 more, 2 pi, 1, 2, 3 more will be 5 pi over 2. 1, 2, 3 more will be 3 pi. Okay, so this one, we are going to have the period is really double the period of the parent function, so we should expect it to be twice as wide. So my asymptotes are going to be at pi, and 3 pi. Now, if we remember, right in the middle, there is an intercept. Now, typically, don't write this, but typically tangent would come down and to the left like this. However, it's going to be reflected in the x-axis, so my tangent function actually looks like this. And then 1, 2, if I go back the other way to try to squeeze one more in, 1, 2, 3, negative pi would be out here. From negative pi to pi is another 2 pi radians. So I could put an intercept there. I would have another asymptote out here. And there would be 2 cycles of the tangent curve. Okay. Let's look at example B. The tangent of x minus 3 pi over 2. So we're going to list the characteristics with VAP, V-A-P-S-P. There's no vertical translation. Amplitude is 1. For my phase shift, I'm actually going to do my phase shift here. It's x minus 3 pi over 2. And I'm going to first set that equal to pi over 2. And then x minus 3 pi over 2, and set that equal to my second asymptote for tangent, 3 pi over 2. Okay, so when I add 3 pi over 2 to both sides, I get x to be 4 pi over 2, or 2 pi. And here, when I add 3 pi over 2, I get x to be 6 pi over 2, which is 3 pi. So this does not have a period change. As you can see, if I go from 2 pi to 3 pi, that's just 1 pi. So the period remains the same, but there is a shift, definitely a shift. So the period should be just pi, and if I do the formula for pi, it would be just pi over b, and b is 1, x, so that would just be pi over 1, or pi. Okay, so when I did these, I did the same type of scale as with the other one. I did every 3 was 90 degrees, so 30, 60, 90, I did pi over 2. 30, 60, 90, there's 3 pi over 2. I mean pi. Sorry. There's pi. And then 30, 60, 90, there's 3 pi over 2. 60, 90, there's 2 pi. Okay. And again, this was a scale of 30, which is pi over 6. So we've counted by pi over 6s. 1 pi over 6, 2 pi over 6, 3 pi over 6 is my pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6 is pi, 7 pi over 6, 8 pi over 6, 9 pi over 6 is 3 pi over 2, 10, 11, 12 pi over 6 is 2 pi, and we're going to keep going because I need to go all the way out to 3 pi. I need to make sure that I have 2 pi and 3 pi on here. So then from, if I'm in 6s, that's 13, 14, 15 pi over 6 reduces to 5 pi over 2. And then 16, 17, 18 pi over 6 is my 3 pi. Okay, so now I have my new asymptotes at 2 pi and 3 pi from my shift, but now I'm every pi, so every pi radians, I will have another asymptote. So I could actually go back to the left at 1 pi, at 0 pi, so I'm going to be able to get quite a few cycles in here. This is tangent, no reflection, so in the center of the asymptotes, there's always an intercept. And now we'll draw down and to the right our tangent curve. So it's all in shifting the asymptotes and the period. Okay. Now let's look at a cotangent graph. So we want to locate vertical asymptotes and sketch the graph of the cotangent of x over 3, or we can write that as the cotangent of 1/3 x, either one. So VAPP, there is no vertical translation, amplitude is 1. Now the phase shift. For cotangent, I'm going to take 1/3 x and set it equal to my first asymptote for cotangent, which is 0. We just really need to know that from the parent function. That's how I know that. And then 1/3 x equal to my next asymptote in cotangent, which is pi. So as I solve these for x, multiply both sides by 3 here, and x is still 0. And if I multiply by 3 here, x is 3 pi. So we've actually tripled the period. From 0 to 3 pi is 3 pi radians. That should be the period. So my formula is pi over b. b is 1/3. So pi over 1/3, which is pi times 3, or 3 pi for the period. So this is pretty big. I am going to do the same scale of pi over 6. So every tick mark is 30 degrees. And I want to make sure that I get all the way out to 3 pi. So 1 pi over 6, 2 pi over 6, 3 pi over 6. I'm going to label every third one pi over 2. 4 pi over 6, 5 pi over 6, 6 pi over 6 is pi. 7 pi over 6, 8 pi over 6, 9 pi over 6 is 3 pi over 2. 10, 11, 12 pi over 6 is 2 pi. 13, 14, 15 pi over 6 is 5 pi over 2. 16, 17, 18 pi over 6 is 3 pi. So I now have asymptotes at 0. My first asymptote is at 0 from my information. And my second one will be at 3 pi. And right in the middle, I always have an intercept, and cotangent is going to go down and to the right. Now, you could always know that on the other ends of these asymptotes, it's doing the same kind of thing, but one cycle is good enough. In this case, it's pretty big. Okay, we're going to finish off with a couple of graphs of secant and cosecant. So we're going to locate vertical asymptotes and sketch the graph of each function. So the way that we're going to handle cosecant and secant is literally we are going to lightly graph the reciprocal functions sine and cosine, and then from there it will be really easy to create the cosecant and secant graphs. So if I'm looking at y equals the cosecant of x plus pi over 2, I'm actually going to graph y equals the sine of x plus pi over 2, very lightly. Okay, so let's do VAP. Vertical translation, amplitude, phase shift, and period. Vertical translation, there is none. Amplitude is 1. Phase shift, so I'm going to set x plus pi over 2 equal to 0 is where it starts, and x plus pi over 2 equal to 2 pi is where my parent function for sine ends, and I'm going to solve those. So I'm going to subtract pi over 2, and x equals a negative pi over 2. So just as we thought, my phase shift is actually pi over 2 to the left, negative pi over 2. That would be my phase shift. And then if I subtract pi over 2 here, realizing that 2 pi is 4 pi over 2, I get x equaling 3 pi over 2. So this is my new start and my new end. And from negative pi over 2 to 3 pi over 2, hopefully you can see that that's a distance of 4 pi over 2, which is 2 pi. So if we go over here and do the period formula, the period for cosecant is 2 pi over b, which is 1, so the period is just 2 pi. Okay, so now we're going to create a scale, and our amplitude is 1, so I'm actually going to go up 3 units and mark a 1, go down 3 units and mark a -1. And you can go up 4 if you want, that's no problem. Okay, for this one, I'm going to use the same scale of pi/6 or 30 degrees, and I'm going to label every third one, so every 90. So this would be pi/2, and back this way is -pi/2, because that's actually where we have to start. And then we have pi, 3pi/2, and 2pi. So with this, remember, I'm going to create a midline, which has not changed. So my midline is actually, let me use a lighter color. So my midline is still at the x-axis. Because remember, right now I'm still graphing the sine curve. The top of my box will be 1 unit up, so up here at 1. The bottom of the box will be down here at -1. Now the left side of my box will be at -pi/2, and the right side of my box will be at 3pi/2. So there's my box. Now I'm going to draw one perfect sine curve inside that box very lightly. So remember, sine starts in the middle, it ends in the middle. In the middle, it's in the middle. Now halfway between -pi/2 and pi/2, it's at the top at 1. And halfway between pi/2 and 3pi/2 at pi, it's at -1. So with a light dotted line, there's my sine curve. Okay. So now that we have sine, you don't have to. I'm going to go in and just erase part of this box because there tends to be a lot of dotted lines running around. So I'm going to just take some of those out of there. So there is sine, but what we want to draw is cosecant. So to draw the cosecant, we are going to create, let's make a note of this before we write it. I'm going to shrink this down a little bit, maybe get this out of our way, and make a note of what happens. So with these two functions, where the sine function has x-intercepts, that's where the function is 0, and that's again where it touches the middle. The cosecant function will have asymptotes because the reciprocal of 0 is going to be undefined. Okay, so this is kind of important information, and we're going to just say same for cosine and secant that we'll do in just a minute. Okay, so knowing that, now we're going to take a look. Wherever I have intercepts for sine, the cosecant function will have asymptotes. And again, this could just keep repeating. And so then what we know, the way that we're going to draw this is simply by knowing that the peaks and the valleys share. The reciprocal of 1 is also 1. So we're going to share this right here, and you can put arrows on those. And the reciprocal of -1 is also -1, so it's going to share the bottom. And there is one cycle of the cosecant of x plus pi/2. Okay. The last one will be secant. So the reciprocal function for secant, of course, is cosine. So we're going to look at drawing the cosine of 1/4 x. And then once we have that lightly graphed, we'll graph the secant. So VAP, vertical translation, there is none. Amplitude is 1. We're going to look at the phase shift. Did I double check the period on that? Yes, I did. Okay. We're going to double check the phase shift, or do the phase shift and double check that with the period. So the phase shift for cosine, I'm going to take 1/4 x, set it equal to where cosine starts, 0, and 1/4 x and set it equal to 2 pi, which is cosine's normal finish. Multiply both sides by 4 on the first one. X is still 0, So this is going to be where it starts. And multiply both sides by 4 here, and x is going to equal 8 pi. This is going to be where it ends. So again, this means that our secant graph is going to be 4 times as long as normal. If it's 1/4 x, it'll be 4 times as long. Okay, so my period then is 8 pi from 0 to 8 pi, and the formula would be 2 pi over 1/4, or b, and that of course is 2 pi times 4, which is 8 pi, would be my period, so that confirms it. Okay, since I am going to draw the secant graph using cosine, I am going to go up here and mark a 1, and down here and mark a -1. And now I'm going to create my box. The midline will still be at 0, 0. The amplitude is still 1. Oh, I guess I should label my axes. That would be nice, Ms. McDaniel. Okay. So, I actually, since we need to go all the way out to 8 pi, I did a scale of pi over 2, and I actually labeled every 2 pi. So I went 4, 1, 2, 3, 4, there's 2 pi, 1, 2, 3, 4, there's 4 pi, 1, 2, 3, 4, there's 6 pi, and then 1, 2, 3, 4, there's 8 pi. Okay, so that's a scale of pi over 2, but I just labeled every full revolution, every 2 pi. So 2 pi, 4 pi, 6 pi, 8 pi. Okay, so I have my midline, I have my top, I have the bottom. This is going to, remember, start at 0 and end at 8 pi. So my first, the left side of my box is here at 0, and the right side of my box is at 8 pi. And within that box, I'm going to draw a perfect cosine curve to fill that all up. So cosine starts at the top, ends at the top. In the middle, it's down at -1. Halfway between the first half, it's at an intercept. So at 2 pi, there's an x-intercept, and at 6 pi, there's an x-intercept. So I am going to lightly, with a dotted line, draw this cosine graph. Okay. And then, you don't have to, but I'm going to take away some of these dotted lines from the box, because then we have intercepts that are dotted, and it just makes it a little more confusing. Easier for me to do than probably you on a pen or pencil, with a pencil for sure. Okay, so now I'm going to look at the secant graph. So the secant graph is going to have asymptotes wherever the cosine graph has an intercept. Okay? And so as I do this now, I know that wherever cosine has 1 as a value, it shares with secant. So I'm going to come over here to the y-axis. It's going to share right there. In between 2 pi and 6 pi, it's going to come up, share at -1, and at 8 pi, it will also share. Now, this doesn't mean you couldn't go ahead and draw a full U on both ends. That's fine, but you don't have to do that if you don't want to. Okay? All right, so these are our transformations for cosecant, secant, tangent, and cotangent.